Hi there. Let's go ahead and name some alkenes. And while we're at it, we'll also look at the alkynes, at least briefly here. Um, and also we'll look at cyclic alkenes. So in this table, there are three examples: an alkene, an alkyne, and a cyclic alkene. And the first step to naming these is to figure out what the longest contiguous chain of carbons is that actually contains the double or triple bond, and it has to contain both carbons of the double or triple bond to be the parent chain. Okay, so here we have hexene, 1, 2, 3, 4, 5, 6, pentyne, 1, 2, 3, 4, 5, and then we have a cyclic six-membered ring, and so that's cyclohexene. So then you want to locate the double or triple bond using a locator number, like an address. And so that's going to go between the parent chain name, so like hex, and then the ending name, which indicates that we have an alkene. So ENE indicates that we have an alkene, and the 2 goes right in front of it, meaning that the alkene is at the second carbon of the parent chain. So you actually don't need to do that for cyclohexene. We know that the double bond is going to be between carbons 1 and 2. So then as before, as you've named before, you need to figure out what the substituents are, and they should have the lowest numbers possible, but the alkene or the alkyne should actually get priority in that decision about which side to start numbering the chain. And so here the methyl group ends up being on carbon 5 because the alkene has higher priority in naming, and so it gets the 2. Same thing with the pentyne example. With the cyclohexene, we know that the carbons on either side, or either the carbons of the alkene, are going to be numbered 1 and 2, and the one that gets the 1 is designated so that the substituents have the lowest numbers possible. You do always number 1 and 2 across the double bond, so you can't like call this 1 and then go the other way. All right, and then finally, you do need to add some stereochemistry, and 2 of these do have stereochemistry to add. This first one we'll come to in just a second in the next slide and the slide after. And then here the stereochemistry is this S chirality center. All right, so you probably remember cis and trans, and cis is where you have your 2 substituents on the same side of the double bond. Trans is where they're on opposite sides of the double bond. It's as if you drew a line horizontally right over the double bond. So cis methyl groups are on the same side, trans on opposite sides. Cis and trans are really limited in their scope. You usually only use them if the substituents on either side of your double bond are really similar. If they're different, then, or if you have 3 substituents or 4, then there's still multiple isomers that you can draw, but cis and trans don't really help you do that. So we need a different way of designating them, and we actually use the same rules for priority that we used when designating R and S. We use the Kahn-Ingold Prelog rules for priority. So here is an example of that. Let's see here. My slide has moved over a little bit, so let me get it back on here so you can see it. There we go. Maybe there we go. All righty. Oh, that was wrong. I have my text bar in the wrong place. All right, in any case, sorry about that. Naming with E and Z. So here is an example of an E isomer. And the way that you figure this out, the way that you get this, is a 2-step process. And in the first step, you draw a vertical line down the middle of the alkene. And then you compare the priority of the two substituents on the carbons on each side of this double bond. And so on the right side, there's a carbon that is a substituent and a hydrogen. And so a carbon, because it has a higher atomic weight, has higher priority than the hydrogen does. And so it gets the number 1 and hydrogen gets number 2. If we move to the other side, we see that there is a methyl group on the top and an ethyl group on the bottom. The carbons are the same in both cases. That doesn't help us. So we have to move to the next atom and compare them. And we have a carbon here, a hydrogen up here. And so the ethyl group has the higher priority, methyl is lower priority. Okay, so that's the first step. Now we go over to step 2. And in step 2, we erase this vertical line, and instead we have a line that goes along the double bond, like that. And we compare the groups on opposite sides of the double bonds. And so if we look on the top, or top right, we see that there's a number 1 and a number 2. And if we look on the bottom, we see there's a number 1 and a number 2. So as it says up here, the number 1s are on opposite sides of the double bond. And so whenever that happens, when the number 1 groups are on opposite sides of the double bond, then we call this an E isomer. If they were on the same side, if the 1 was down here, and the 2 was on the top, we would call that the Z isomer. So oftentimes people will remember that by Z-Zame-Zide. Makes me laugh every time. All right, so you'll just want to practice naming with E and Z to figure out and make sure that you can do that process. It really is learning how to do a process where you do first one step and then the next step. So let's just figure out finally, or let's just end here with a little bit about alkene stability. And you might remember hyperconjugation, where carbon-hydrogen bonds or other bonds that are adjacent to p orbitals can actually donate a little bit of electron density to that p orbital. And so that's what happens here, is that the more methyl groups or more carbon-hydrogen bonds that you have adjacent to your alkene, the more of a little bit of tiny bit of overlap that can happen between your various orbitals as the bonds, as the carbon bonds kind of rotate around. So, and I don't mean, pardon me, I don't mean that the alkene is rotating. I mean that the methyl group might be rotating around. And as soon as one of those carbon-hydrogen bonds aligns with the alkene p orbital, there can be a little tiny bit of orbital overlap, which is stabilizing. So the more of those R groups that you have, the more of that little bit of stabilization that you have. And so stability of alkenes increases the more groups you have, the more substitution you have on your alkene. And also note that trans is usually a little bit more stable than cis is due to sterics.